All right, so as we talked about a little bit, this class is dealing with geomechanics. Classically, this was called rock mechanics, and I talked a little bit about why that's changed, because the wording has changed, because we also include man-made materials, concrete, cements, other synthetic materials, man-made materials that behave like rocks. And when I say behave like rocks, the sort of main difference between the way rocks behave and the way another engineering structural material would behave is that their rocks are heavily pressure dependent. Right? So again, down in the earth where they're under a lot of confinement pressure, confinement stress, they behave differently than they do at the surface where they're unconfined. Right? So that's one key difference, and we'll talk about how that confining pressure works on rocks, right? So, the other key word in there is mechanics. Right? So mechanics typically deals with, when we think of mechanics classically, you're really talking about the formulation and solution to the problems that deal with Newton's second law, right? F equals ma. You've all had statics, so that's like F equals 0 in that class, right? And for the most part, when you took statics, every structural thing in your analysis was a rigid body, typically. And then when you take solid mechanics, you learn that those rigid bodies are in fact not rigid, but they're deformable. And the way we compare the deformation between, a leg of that chair and a leg of the 360 bridge, right, which are on a vast scale different from one another, is we normalize them by the area, right? So if we apply a force, if I sit on that chair, then we normalize my weight by the area of the leg, and then we call that stress. Right? And same thing, when a car drives over the 360 bridge, it applies a force to one of the, that's a suspension bridge. There's no legs on that bridge. Anyway, but some bridge that has legs on it, South Congress Bridge, right? When a car drives over, it applies a force to it, then we normalize that force by the area of that leg, and then that's a stress, and then we know something about the mechanical behavior, the relationship between stress and strain, and that tells us a little bit how the material is going to deform. And ultimately, as engineers, usually, like if you're a mechanical engineer, you want to design things that don't deform too much, or certainly don't deform to the extent that they fail. It turns out that in petroleum engineering, all the important mechanics we care about involve failure, right? Or large deformation at least, right? Hydraulic fracturing, subsidence, other things like that, right? So we're going to include in our definition of mechanics or geomechanics the field of fracture mechanics. Right? So we're going to learn a little bit about how materials fail, right? Fracture. So, I gave a little bit of partial formal definition of stress, and that, it's a force divided by an area, right? But we don't really need that. We can talk colloquially about stress. Most of us know what it is, right? We certainly know what pressure is. Right? Swim down to the bottom of a pool, right? You feel your ears hurt more, right? That's pressure on your ears. That's the stress, right? They have the same units. Force divided by area. When you have fully continuous bodies, we take those areas, the area of that leg, we take them and make them differentially small, right? And then we end up something called a stress tensor. And we'll talk about that in this class, because we need actually, the full stress tensor, which is sort of a three-dimensional definition of stress, in order to analyze the stresses in the earth. And it's ultimately the stresses in the earth that we care about most in this class, right? And so we'll have a little bit of lecture to talk about where those stresses arise from. And principally they arise from tectonic motion, right? So there's natural in situ stresses in the earth everywhere that, for the most part, are there because of tectonic motion, the motion of the plates. There are other mechanisms, but for the most part, stresses arrive due to tectonic motion. So, a little bit more about why stress is important in petroleum engineering, and for here I have a couple of specific examples. So, again, like I said earlier, even though you may not think mechanics is important in petroleum engineering, it turns out we have to drill a hole in the earth to get the fluids out. If you can come up with a better way, I'd be interested to know. But right now, we have to drill a hole in the earth. And anytime you drill a hole in anything that's under stress, there's a stress intensity associated with the far field stresses, right? So do you guys remember in solid mechanics, did you look at problems with like a hole in a plate problem? Did you look at that? Did you analyze that problem? So anytime you have a far field stress, anything with a hole or any kind of defect in it, turns out that there's a stress intensity due to the fact that the hole is there. Right? And so that stress intensity, in this case our hole is a wellbore, that stress intensity can cause the stress in that region to exceed the strength of the rock, and the rock can fail. Okay? If it fails, and these are sort of an example classically called breakouts. Right? So these you see bits of material starting to crack and fail, and if this flakes off into the wellbore, there's almost every wellbore in the world has some breakouts in it. And just because you have a few breakouts doesn't necessarily mean you have an unstable wellbore. Right? So an unstable wellbore is when you have essentially breakouts all around the well, such that the integrity of the circle or the wellbore itself can't be maintained, and you get sort of continuous material falling down on the bottom hole assembly. Right? And then that can be a very bad thing if you're trying to drill, because you have to get that material out of the well. And so in that case, if you had an unstable well, you'd have to set casing, right? Do something. You have to do some correction mechanism. Deviate the well, set casing, do something, right? So if we understand about the mechanics of when we're going to have unstable wellbores, the stresses in the earth, and the wellbore stability has a lot to do with, especially in horizontal drilling, the direction you're drilling with respect to the principal stresses in the earth, right? The in situ stresses in the earth, the strength of the rock, other things, right? So if we understand all that up front, then we can design a smart plan a priori, right, before we go and drill it. And hopefully the most efficient one would be, setting the least casing and all that, because it's an expensive process. And if you have to deviate a well or set casing in the middle of drilling, in an unplanned way, that can be very expensive. Right? Another thing is we're going to study in this class, and really this is kind of where we start, because it's sort of the simplest thing, is with respect to fault slipping. Right? So the big thing in the news now with respect to hydraulic fracturing, they've kind of given up on the groundwater contamination, and now it's earthquakes, right? Well, it's not, in fact, the hydraulic fractures causing that. It's injection of wastewater disposal. That's the amount of wastewater has gone up a lot in the presence of hydraulic fracturing. And so, particularly in Oklahoma and North Texas, where there are some large faults in the basement rock, continuously injected at high rates, lots of fluid, and that fluid increases the pore pressure, right? So in reservoir simulation, we talk about depleting pore pressure because we're taking it out, right? All right, but in an injection well, you're injecting or disposing of wastewater, increasing the pore pressure. When you increase the pore pressure, you increase the normal stress on the fault, so the sort of, whether a fault's going to slip or not is dependent upon the forces resolved on that fault. So how much normal force, the force sort of holding the fault closed, versus how much shear force, and the friction factor, which is a material property of the rock. Right? So if you increase the pore pressure due to fluid injection, you're basically releasing the normal force, and if that exceeds some criteria, the ratio of the normal force to the shear force with respect to the friction coefficient, then you could have a fault slip, right? So that's what happens in induced seismicity or these earthquakes that are generated by injection wells. Of course, this also helps us in the production, right? In what we believe why shales produce the way they do is because when we produce a hydraulic fracture, we activate lots of mini earthquakes, tiny things like 30,000 times smaller than you could ever feel at the surface. But many tiny slips on natural fractures that are already in the rock. Those slips make those more conductive pathways to the wellbore. And that's one of the reasons we believe that shale wells produce the way they do. Right? So in one respect, the slip can be very bad, earthquakes on large faults, and in one respect, on small natural fractures, the slip can act as a stimulation. Okay, so the other thing is reservoir depletion, right? So if we're producing a reservoir, we're taking fluid out of the pores. Right? In a sense, that fluid is in the pores is holding the rock up. And so if you take it out, you can get a collapse. And sometimes that collapse, that subsidence, can be measurable at the surface. Sometimes it can be as much as a meter or more. When you talk about oil sands and bitumen in Canada, it can be very large. Right? But even in a normal conventional reservoir, there have been measured in California subsidence of a meter due to the production of reservoir fluids. Sometimes the production of the fluids can actually help the production, right? Because what happens is you get something that's called compaction drive, right? So it's sort of like squeezing a sponge, right? You're taking the fluid out, but the weight of the earth on top of it is squeezing more, and you get compaction drive, and it can actually help production. So if we understand that to some extent, couple geomechanics into our simulators, then we can maybe predict or help include those physics and help do better predictions that can possibly help the production and design of reservoir. Right? Of course, subsidence is usually a bad thing. Certainly if your house is on top of it and the earth is subsiding 1 meter, you're not going to be happy. Right? So I think we'll stop here. The next lecture and a half is basically structural geology, which will probably be a review from high school even.